NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve a non-symmetric system of quadratic equations using a clean add and complete the square strategy. We'll walk step by step and keep the visuals simple and intuitive. Here is the system. We will keep all math spoken in words x squared plus y squared equals 2y and y squared plus 1 equals 2xy. Step 1. Add left sides and add right sides. This uses the add equations rule. Step 2. Move all terms to one side, so the right-hand side is 0. Watch the grouping to prepare perfect squares. Step 3. Recognize perfect squares. Each group is of the pattern a squared minus 2ab plus b squared. Now rewrite as squares added together. A sum of two squares is 0 only when each square is 0. So we set x minus y equal to 0 and y minus 1 equal to 0. From the pair we get y equals 1, and therefore x equals y equals 1. Let's box the final answer. Quick verification. Substitute x equals 1 and y equals 1 back into both equations. First equation becomes 1 plus 1 equals 2. Second becomes example. We will solve a system of quadratic equations and then verify the solutions graphically. The system is 2x squared plus y squared equals 24 and x squared minus y squared equals negative 12. Step 1. Add the two equations to eliminate y squared. That gives 3x squared equals 12. Then divide by 3 to get x squared equals 4. Taking the square root, x equals plus or minus 2. Step 3. Substitute into the first equation to find y. 4x equals 2. 2 times 2 squared plus y squared equals 24. So y squared equals 16, and y equals plus or minus 4. 4x equals negative 2. The same calculation gives y equals plus or minus 4. Therefore, the four solution points are 2, 4, 2, negative 4, negative 2, 4, and negative 2, negative 4. Now, let's confirm visually. The first equation is an ellipse. The second is a hyperbola that opens up and down. Their intersection points should match our four solutions. In this lesson, we will solve a system consisting of a quadratic and a linear equation, showing every step clearly and also visualizing the two curves and their intersection points. Example, solve the system. Y equals x squared plus 6x minus 8, and y equals 4x plus 7. Step 1. The left sides of both equations are the same variable y. Therefore, the right sides must be equal. So we write x squared plus 6x minus 8 equals 4x plus 7. Step 2. Move all terms to one side to set the equation to 0. Subtract 4x and 7 from both sides. We get x squared plus 2x minus 15 equals 0. Step 3. Factor the quadratic. X squared plus 2x minus 15 factors to left parenthesis x minus 3 right parenthesis times left parenthesis x plus 5 right parenthesis. Setting each factor equal to 0 gives x equals 3 and x equals negative 5. Step 4. Use the linear equation y equals 4x plus 7 to find the y values for each x. 4x equals negative 5. Y equals 4 times negative 5 plus 7 equals negative 13. 4x equals 3. Y equals 4 times 3 plus 7 equals 19. Step 5. Write the solution as ordered pairs. The intersection points are left parenthesis negative 5, negative 13 right parenthesis and left parenthesis 3, 19 right parenthesis. To see this geometrically, let's graph both equations on the same set of axes and verify that the points we found are indeed the intersections. We draw the axes, then plot the parabola y equals x squared plus 6x minus 8 in cyan, and the line y equals 4x plus 7 in red. Finally, we mark the two intersection points and label them. Summary. We set the right sides equal because both equations equal y, rearranged to a standard quadratic. Factor to get x equals negative 5 and x equals 3, substituted into the linear equation to obtain the corresponding y values, and verified the solutions on a graph. Therefore, the solution set is the 2 points, negative 5, negative 13, and 3, 19. In this lesson, we will solve a system consisting of a line and a circle. We will first visualize the system, and then follow the algebraic steps exactly as shown. Let us draw a coordinate plane. The circle x squared plus y squared equals 13, and the line x plus 2, y equals 7. This will help us see the two intersection points we are solving for. The circle and the line intersect at exactly 2 points. The first point is 3, 2. The second point is -1/5, 18/5. We now follow the exact algebraic steps. First, from x plus 2y equals 7, solve for x equals 7 minus 2y. The second equation is x squared plus y squared equals 13. Substitute x equals 7 minus 2y into the second equation. That gives left parenthesis 7 minus 2y right parenthesis squared plus y squared equals 13. Expand the square. 49 minus 28y plus 4y squared plus y squared equals 13. Combine like terms to move everything to one side. 5y squared minus 28y plus 36 equals 0. Factor the quadratic. Left parenthesis y minus 2 right parenthesis times left parenthesis 5 y minus 18 right parenthesis equals 0. From the factors we get two cases. If y equals 2, then x equals 7 minus 2 times 2, which is 3. If 5y minus 18 equals 0, then y equals 18 over 5, and x equals 7 minus 2 times 18 over 5, which simplifies to -1 over 5. These two algebraic solutions match the two intersection points on our diagram. Let us highlight them once more. Therefore, the solutions are ordered pairs 3, 2 and -1/5, or the solutions are ordered pairs 3, 2 and -1/5, 18/5. In this lesson, we'll solve a neat little system of equations involving symmetry and rational expressions. We'll proceed step by step, and at each step, I'll explain the intuition behind the algebra. Step 1. Write down the system clearly. Notice that each variable equals the other divided by 1 plus the square of that other variable. Step 2. Multiply the two equations, left sides and right sides, to eliminate the fractions in one go. Left side gives x times y. The right side gives xy divided by the product of those denominators. Step 3. Bring everything to one side and factor. Subtract xy from both sides. Then factor out xy. Step 4. A product equals 0 if, and only if at least one factor is 0. So either xy equals 0 or the bracket equals 0. Step 5. If the bracket equals 0, then the reciprocal equals 1. That means the product of 1 plus x squared and 1 plus y squared equals 1. Step 6. Use non-negativity. Squares are never negative. So each term x squared, y squared, and x squared y squared is greater than or equal to 0. The only way their sum is 0 is if all three are 0. That forces x equals 0 and y equals 0. And that also satisfies the case xy equals 0. In this lesson, we will solve a non-symmetric system of equations step by step, carefully following the provided solution structure. We begin with the example prompt. Here is the system we need to solve. Step 1. Write the system of equations clearly so we see the structure. This is our setup. Step 2. Substitute the expression for x into the second equation. Replace x by y over 1 plus y squared inside. Y equals x over 1 plus x squared. Step 3. Simplify the complex fraction in the denominator. First write 1 plus the square as a single fraction. Then express the entire right-hand side as a quotient of two fractions. Step 4. Multiply by the reciprocal to clear the complex fraction. This gives y equals y times 1 plus y squared, divided by the quantity 1 plus y squared squared plus y squared. Step 5. Bring all terms to one side and factor out y. We obtain y times the bracket equals 0. Step 6. By the zero product property, either y equals 0 or the bracket equals 1. We analyze both cases. Step 7. Solve the second case. Cross-multiply to obtain 1 plus y squared quantity squared plus y squared equals 1 plus y squared. That simplifies to 1 plus y squared quantity squared equals 1. Step 8. Take square roots. we get 1 plus y squared equals plus or minus 1. The negative case would force y squared to be negative, which is impossible over the reals. Therefore, y equals 0 is the only real solution. Step 9. Back substitute into the first equation to find x. If y equals 0, then x equals 0 over 1 plus 0 squared, which is 0. So the unique real solution is the ordered pair 0, 0. In this lesson, we will solve a symmetric-looking system of quadratic equations by turning it into a sum of squares. Here is the system. We will add the three equations, rearrange terms to complete squares, and then use the fact that squares are never negative. Step 1. Add the three equations side by side. This gives the left sides added together equals the right sides added together. Now move the right side to the left and group terms to complete perfect squares. Notice each pair forms the pattern as squared minus 2ab plus b squared. Each grouped expression is a perfect square. So the left side becomes the sum of three squares. Here is the key idea. A square of any real number is never negative. The only way a sum of non-negative numbers equals 0 is if each one equals 0 by itself. Therefore, each squared difference must be 0. That gives x equals y equals z, and z equals x. Hence x equals y equals z. Let all three variables equal a single parameter t. Substituting x equals y equals z equals t into any original equation gives 2t squared equals 2t squared, which is true for every real t. So the complete solution set is all triples where x, y, and z are equal. In set notation, it is the set of all t, 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 with t real. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.